Hi and welcome to our talk on adopting new methods for old systems. I'm joined by Natalie Bowcat, who's the Senior Construction Engineer. She worked on East Village Plot N08, where we have the Rising Factory. My name's Sophie Drury, Construction Manager. I've worked across both East Village N08 and then moved on to the second project, which is East Village N06. So what are we going to talk about today? How have we stepped away from traditional construction? How are we creating buildings from a kit of parts, and how we will build with less waste, less vehicles, and a tighter programme.
Hi everyone, thank you for joining us wherever in the world you're dialing in from. It's a pleasure to have you and it's a real honour to be here. So my name's Natalie and my pronouns are she, her. So as Sophie said, we both had the privilege of working on the Mace Jump Factory project. Those of you who are in London may have actually seen the Jump Factory looming over London. It was basically what looked like, I guess, two giant bouncy castles or sort of giant structures, white structures on the top of two towers, and could be seen from across London through 2017 to 2018. Next slide, please, Soph. So what the Jump Factory was essentially a means to an end. So the Jump Factory itself was essentially, well, we had two factories and basically they were entire fully functioning working factories. Each factory was over 600 tonnes of steel working weight. They had two gantry cranes. We had a 30-tonne main crane with a 100-metre rope that could extend all the way down to ground level, which obviously you needed as the factory climbed, and a 15-tonne slave crane. They were fully enclosed and clad in a PVC membrane. Each factory had 3 trailing decks for cladding activities to occur lower down. We had loading platforms that could take an entire 20-foot shipping container, so trucks could drive underneath and the container could literally be shackled on to the lifting gear, and the gantry cranes would lift them all the way up and drop them in place on the loading decks. We had 250-tonne jacks in the corner that supported the factory and helped it climb up every week. And we had a 55-hour floor cycle, which in London aligns with the working hours of 10 hours a day on Monday to Friday and then a half day on Saturday. So like I said, the whole function of the factory was to build the two towers. So these were there was a 26 and 30-storey residential tower in an area of London called East Village. And East Village was started off as the London 2012 Olympics Athletes Village, and then was converted into residential properties in the forms of social, affordable and private housing. The whole purpose of the factory was to support a modular structural system. So basically almost like a flat pack system of parts. So the typical floor plate, which you can see on the slide, consisted of twin wall cores, and Sophie will talk to you later a bit more about what they involve. So we had the highest at that stage twin wall cores in Europe. We had precast floor system, and you can see the planks laid out there, the numbered grey squares. They were stitched together with a concrete topping, precast stairs and columns, modular services, so we had modular risers and horizontal distribution elements dropped in place, bathroom pods and prefab utility rooms, so they were also dropped in place by the gantry cranes, and a unitised cladding system. And the only change we made to the tower structure was the 4 corner columns. Because the factory weighed so much, we needed some really strong columns to take the load into the structure because they were carrying the weight of the factory. So they became steel instead of concrete, and we turned them into twin UC columns. But we made sure that they still fitted within the footprint of the corner columns, so that we didn't lose any net lettable area. So why did we go down the Jump Factory route? Well, as we said, it improves the programme. So the idea of the Jump Factory was to improve the programme by up to 13 weeks. And it did that by having a sealed building, basically 4 floors below what we called a working deck. So whilst the floor-to-floor cycle was fairly similar to a conventional structural floor cycle, it meant that four levels below we'd zipped up with the cladding and we were watertight and we could start with the dryer trades. Having internal cranes also reduced the amount of windage off that we had, which is a real problem when you're using tower cranes. It had very obvious safety improvements. Falling from height is a big killer in construction and one of the more serious activities. So by having a fully enclosed factory, you are basically protecting people at height, but also ensuring stuff can't be dropped onto the ground level. It supports sustainable development. You've obviously got a quicker build time, so the impact on the surrounding neighbourhood is less. It supports modular and offsite construction, which is obviously more efficient, and it supported a just-in-time delivery system, so it minimised vehicle movements on the road. So apologies for the slide, it's probably not very clear, but it's a typical cross-section through the jump factory. You can get an idea of the scale of it. So the jump factory oversails the building, so it completely envelops the building. At the top, you can see the gantry crane, and you've got quite a big area under hook there. So we had the top deck, which was the working deck, which was where all the precast elements got laid out and concrete was poured. Below that, we had a propping deck until the concrete stitched it all together and we could strike. We had a screeding deck, we had a cladding deck, and then once the cladding had been completed, we had a GRC deck where the all the sort of dry elements were loaded out from the loading gantries, and all the internal fit out could finish. So it was quite a lot of steelwork. Like I said, it was 600 tons, and you can see the skeleton, if you like, on the left. But the image on the right shows you the actual main elements of steelwork that were doing the work. So we had 2 pitched roof trusses, and they supported the roof structure. We had 4 corner, what we called truss columns, and they sat on the 4 corner building columns and took the load into the building. And then we had a ring truss, which we call it, the horizontal truss on 4 sides that tied all the elements together and also supported the gantry cranes. And on this slide, you can see all the elements being installed. You can see very clearly in front of you the pitched roof truss, and you can also see the yellow, which is the gantry cranes. So just quickly, like I said, you've got the factory sat on 4 corner jacks, and those jacks jacked up every week and the whole floor cycle started again. In order to jack them, the corner columns were attached to a climbing bar, and that climbing bar was then fixed through into the structure. So that climbing bar was used to jack the structure, but also in the temporary phase, in the phase when we're actually not moving the structure and taking the load into the building, we had a bracket that was fixed onto the structure, and all that load was secured through the bracket by a pin. So a pin slotted between the climbing bar and secured the factory itself basically into the bracket via a high strength steel pin. So the design of the factory was quite complex. We had over 600 load combinations that we needed to consider, and we considered all possible arrangements of live and crane loads. So the factory was designed that we could still, in theory, operate in storm wind conditions. We didn't, in fact, actually do any lifting in those conditions, but you could still continue with works on the enclosed deck. And we also considered possible failure modes, such as what happened if a jack failed. So the high strength steel pin, which I talked about, weighed 250 kilograms. And that basically was the linchpin, which took all the load from the factory into the building structure. And you can see one of our construction managers on the left to give you an idea of the scale of the pin. And on the right, you can see how the pin, it's probably not the clearest picture, but that's where the pin links through the bracket. The bracket is grey, and the climbing bar, which is the white bar with holes in, locks between the brackets, the two parts of the brackets, and that pin secures them all together. And we actually needed a hydraulic arm to be able to move it in and out, particularly to remove it, because you've got the load of the factory coming down onto a pin, and it needed to be taken out under load. So that's the bracket there. So as you can see, it's got two parts to it, and there's a gap in the middle, and you can see the hole through and lock the climbing bar into the bracket. And that's one of our engineers. Again, just to give you an idea of the scale. Each bracket weighed around 5 tons. So we used Dorman long jacks, and this just gives you an idea of the jacking mechanism, how the jacks pushed up the climbing bar and allowed the factory to climb. Each jack had a capacity of 250 tons. It lifted in 500mm strokes, and they were all linked by a manifold. And the jacking cycle takes less than an hour. And it's actually a really, really quiet process. It was quite an eerie thing to be working on one of the other decks and to see the factory just sort of very, very silently and slowly glide past you. Certainly an experience. So this is just a snapshot of the working deck. In the far corner, that red and white thing you can see is actually one of the jacks. You can get an idea for the scale of the factory. In the middle there, you can see the rebar from the precast core elements, the twin walls. And you can actually see some of the white structures, or the white elements there are the bathroom and utility pods that have literally been dropped in place. And then we put in the false work to receive the precast floor planks, and we close up that floor. Again, this is a snapshot of the working deck, so you can see the crane operator there moving the cranes around. They loved it because normally they'd be standing out in the freezing cold, and they were in a warm, dry deck with a little battery pack just manoeuvring the cranes around. So on the left, you can see it skipping concrete into the twin wall, although we eventually decided to pump it in. And on the right, he's lifting, it's not so clear, but lifting in precast planks into place. And this is a view looking up at the factory. This was taken by our resident photographer, Frank De Silva, who was also a neighbour and a photography enthusiast. So the timber that you can see are the loading platforms that can take an entire shipping container. And again, that's the stillage being lifted up through the front of the factory. The biggest success of the factory, which I'm sure Sophie will talk about in her section, was the modular MEP, particularly what we called the H frames. So we had an H-shaped distribution route within the core, and these frames came as like steel frames dropped in place with all the services inside. So as soon as the twin walls went up, an operative was screwing on brackets to take these, and they were dropped in straight away, and then the next level's precast floor installed. So you could literally then come along and just connect to the services to the apartments. So would we do it again? Unfortunately, we haven't done it again yet, but that's not to say we won't. It was definitely an interesting project to work on, and we did learn a lot of things as we went. We had some very, very good things about the factory. We had all the site teams loved working with it. They loved the fact that it was a nice, dry and closed space to work in, and also the fact that once we got going and the team started to work together, we sort of improved on floor cycle each week. There were some really good benefits from it. We would change things if we did it again. The installation and dismantling we would make easier. Unfortunately, because of the nature of the permanent work structure, we weren't able to jack back down, and that is something we would really like to do next time. We had a 9-story link building that stopped us doing that. But you can see on the picture we've got tower cranes on the roof that we had to use to dismantle it. We would also reduce the number of hanging components that we had. We had 3 levels of hanging floors, which weren't utilised as much as we would have liked to have done, and was quite heavy steel work. So we would probably rationalise that and have something more akin to the trailing deck that you would get on a slip form. But on the whole, we learnt some very, very valuable lessons, particularly about modular and off-site construction, and that's what Sophie's going to talk to you about next. And just a quick point I'd like to leave you with, we'd like to thank obviously our clients, because without their support we wouldn't have actually been able to trial the Jump Factory, and then obviously the successive project, which is the HRS scheme, on the N08 and the N06 projects, which are sister projects. So we're really grateful to them for their support. Thank you.
The next steps, Mace Tech. Thanks, Natalie. So what were the next steps? How did you make the Rising Factory more efficient than it was? And what have we learned, and where could we go from there from East Village N08? We were lucky enough to win the next phase for Qatari DR and Delancey in East Village. 524 apartments across 2 towers with a sky bridge and 2 tail buildings. So again, we haven't got the ideal tower without any ancillary buildings, but we've got all the ideas behind the componentization that we got from N08, and we needed to find a way to use them on N06. The biggest challenge on site at N08 was the physical construction of the Rising Factory. The erection and the dismantle were key to making the project a success. The real question was, how could you streamline what we had already achieved at N08, and how short could you really turn around a cycle? Moving on from N08, we were going from the 55-hour week to the 1% gains. What can we change? How can we improve? And how can we move forward?
We're at East Village, which is a legacy site from the London Olympics, and behind us is one of the last phases, N06, which is a private rented scheme for Get Living London.
We're bringing in 525 new homes to add to the nearly 2,000 homes that we've already got here at East Village at the Olympic Park.
N06 basically is a residential building. The thing that makes this different is the build methodology for the towers.
We are attaching the facade to the slabs before we bring them onto site, and we bring them in a module, which is then landed on in one. So as soon as your slab goes onto the deck, you also have your facade fully fitted.
HRS is an optimised logistical solution. So the first thing we do is look at the size of components that we can safely ship to site and lift into position. Once we've worked out the modularisation, we then review the engineer's design and make sure that they can all be done in the right size components for the platforms. When we assemble all these units, we put them into a BIM 360 modelling, and that enables us to track it from design through manufacture, dispatch and then delivery to site. So we know where every component is every step of the way.
Mace built N08, which is 482 apartments just over there.
And the project N08 was where we pioneered our Jump Factory, and the lessons we learned from the Jump Factory really allowed us to understand the benefits of componentising the construction process.
What we're doing here is a first in the UK, and it's a really exciting thing to work on.
On site we get the floor plate prepared, so we use a multitude of different propping systems. We get them all set so that we have a just-in-time delivery of the unit, lifted up in a very quick time and landed onto these preset props. That then creates the working platform very quickly for the labour up on top.
We also have bathroom pods and utility cupboards that come in and get landed. And by that point you're also working on doing all the final touches to the rebar, lining and levelling the facade, and then you start the next process again.
The benefits of Mace Tech are that it will drive the very, very fastest program, because we can predict so accurately exactly how long it takes to install every single component. So program delivery is not only significantly faster, but it's guaranteed.
Our total aim for a completely enclosed floor, we're targeting 5.5 days. Now we believe we can actually achieve a quicker time than that, but our first goal is 5.5 days.
At the end of every week we've got a full floor that we've built. Everyone can turn around and physically see that we're really making progress at the building.
I actually believe that the method that we're using is the way forward.
It's great to see that we're pushing the boundaries on health and safety off-site.
we're giving them quality you cannot deliver on site. And we know that because we've done it. But taking the working at height risk away from the guys and girls who work in our job every day, that gives me a warm feeling that we are thinking in a way to protect others.
We don't need the design of the building to be bespoke for modularisation. We're able to take the design of any building and just put it together in a smarter, faster way.
When I look at what Mace are doing and the way I think they're really innovating and to some extent disrupting the sector, I think from a client perspective, we absolutely applaud that.
From the client, they get a better product, they get a better journey, they get more certainty. For me, it's a win-win.
So similar to NO8, at NO6 we have several key components that form part of our floor build. As you saw in the video, the slab and the facade are delivered as a module. Following on from this, we also have precast columns, twin wall, which are essentially two precast panels knitted together, which slide over starter bars on the slab. Solid walls, core boxes, which form risers and lift shafts. U-slabs, which have the core slab with the horizontal services module prefixed off-site. So that's the module that Natalie was talking about earlier. We now have that pre-installed into the slab, saving us a key 3 lifts on site. Bathroom pods, utility cupboards fitted out with even the Wi-Fi router, and again the vertical riser modules which carry all the mechanical and electrical services up the building. And you can just see sort of the neat picture there of all the bits that we lift in as part of the working deck. So NO6 started well ahead of our start on site. When you've got a building that's a kit of parts, you rely heavily on early design and coordination. We then had to procure and manufacture ahead of a usual construction project, essentially creating a supermarket of elements which have to be assembled off-site and then delivered to site just in time. Each floor is broken down into components, again very similar to NO8 but with some slight tweaks. You can see here how a typical slab is formed into components. A lot of work went into this, and it started well before I joined the project. Each slab has pre-formed holes for services, and opposed to on NO8 when we had full Omnia deck, here we only have what we refer to as stitches, which tie the slabs together, reducing the requirement for steel tying and the amount of concrete which needs to be poured on site. So each slab has more than just penetrations. It's probably quite difficult to see it in this picture, in this drawing here. We have locators for prop heads included in the design, sleeves for column dowels, connecting the two columns to each other from each floor, lifting sockets, and even half-inch channels for the balconies on the lower levels. Now we're at 25 stories high, it's easy to forget how important each one of these elements are. And looking back, I remember how much effort it took to make sure they work together. The slabs themselves are set out according to the locators, which are precast into the slabs, and this then sets the geometry of the building, with a key dimension from the slab locator to the facade, which allows for a really quick and efficient on-site installation. So one of the key elements of making sure we achieve the 5-day cycle is to ensure we know what we have in our supermarket. It's really critical to know that each supplier has sufficient stock of the elements to ensure that we do not lose momentum. One element missing can hold up an entire floor, whether it's a column or a utility cupboard. We need to achieve 100% of the cycle in order to make sure that we can start the next cycle. With one piece missing, we can't carry on. And if you use columns as an example, there are 21 columns per floor, and we're running 2 towers at the same time, and we run 4 floors per tower per month. So that equates to roughly, to 168 columns a month, which we need to have available and in stock. So you can see how if we don't keep a close tab on our stock, we would then run into trouble pretty quickly. So here we have a few pictures of what we affectionately call our supermarket. On the left, you can see a slab with the stitches being cast into them. Then to the right, you can see the slabs stacked and ready to be picked to have the facade attached to them. And below, you can see the gantry crane used to lift and move the elements. And finally, on the right, just the stack of columns that we have waiting to be brought to site. In these pictures, you can see the installation of the facades on the slab, and this was, again, one of the really key things that we wanted to preserve from N08 was reducing the need for working at height, which we've done by creating these modules off-site. And what you'll notice is that the guys are stood on the floor whilst they're installing, apart from one guy who's in a scissor lift. Each slab is loaded out in preparation for the next floor's worth of modules, and then our facade team moves in and sets about installing the facade ready to be brought to site. We also have a team who do quality checks prior to each unit travelling from Brandon to our project, and this reduces the requirement for on-site snagging once they've been installed onto the building. And here is a short video showing the assembly yard in action. So that video just shows you, it's a time-lapse video essentially of how we're building our towers on the ground. So after design, the next critical element for a successful cycle and a kit of parts is logistics. We rely heavily on our logistics team to ensure we can run a smooth downside. Without deliveries arriving through the gate as and when they are needed, we would not hit our daily installation targets. And as I said earlier, if you miss something, you then can't continue on to the next cycle. On-site installation. So once they're through the gate, it's down to the on-site installation team. On a project where so many elements are lifted and installed, the key team is really your lift team, and they have the ability to make or break a cycle, and it's their enthusiasm that really has managed to get us down from the 55-hour to the 50-hour sequence. So we managed to beat that 55-hour cycle and now comfortably run a 5-day cycle. And here's a video showing you what we get up to in a working week. So what's next for us? Well, we're going to be taking pods one step further and trialling a couple of kitchen modules, which is really exciting. Lifting a fully kitted out kitchen into the shell and core sequence is a massive gain on the fit out programme. We also have developed some pre-serviced walls, which we are running with on a couple of floors of one of our smaller buildings. Pros and cons. No on-site assembly means a shorter learning curve and will mean a swifter closeout. We've shaved off half a day from the cycle. and we've managed to reduce the number of lifts by the crane and vehicles through the gate. What's the main con? Rain and wind. Never underestimate the joy of working on a high-rise building in the middle of winter in a very large tent.